Thank you for coming and welcome to Rondaxe's second webinar in a series of webinars introducing and discussing our lifecycle knowledge-based tool called SimpliDATA. In our first webinar, we covered a wide range of the functionality in the platform and briefly detailed how the software covers and helps solve some of the questions brought to us at DCAT. But today, we're going to delve into process fit, why it is important to communicate it properly, quickly, and accurately, and why SimpliDATA should be your choice to do this correctly. So what are we going to show you today? Well, we're going to show you how SimpliDATA can align real-world equipment to your process and gauge your output goals. We'll display our batch plan feature that helps easily define and transmit the information you need for success. And we're going to show how you can evaluate capacity with step-by-step volume measurements that clearly states equipment requirements that are right for your process. I'd like to introduce our CEO of Rondaxe, Ken Schultes, again. And just like in our first webinar, Ken will guide you through the platform so you can see how SimpliDATA can be a fit for your business success. Ken?
Thank you, Dave. So today, what we're going to talk about is an example from the bedaquiline process. Bedaquiline is a tuberculosis medication. It's now generic. That's made in tens of tons per year. And what we're going to talk about is one of the first steps in that process. It's NBPPA, PPPA, got to get the number of P's in there, or N-bromophenylphenylpropanamine, which I will shorten, thankfully, to PPA from now on. And it's made from hydrocinamic acid, or HCA shortened, and bromoaniline. So it's let me just show you the structure here so you can see what's going on. So you're making this acid chloride using thionyl chloride and catalytic DMF to make this acid chloride HCC, contacted with bromoaniline from the solution to reverse charge to it. And this is done with triethylamine in DCM. Everything's in methylene chloride in the beginning for the reaction phase. And here's the final product that we're making in this process. So given that, now we let's do an overview of the process, and it's easiest to do by looking at a process flow diagram. So you can see, first of all, we form the HCC. We do this, and there's some in-process controls to be sure it's done before you proceed. We then bring over the bromoaniline solution into reactor 2, and here we go. And again, we have a process check, and it's possible that it won't be complete after 2 hours. So you hold it, or after the hold period. Then we hold it another 2 hours, and if that's not okay, then you check the scrubber to make sure that it still has capacity to handle off gas, and we charge more thionyl chloride and hold. And then we proceed to the rest of the process. Now we quench the reaction with hydrochloric acid solution, principally to wash out the TEA, but other things too, and completely wash the reaction mix up so that it's ready. Then we proceed to concentrate it and flush the solution over to methyl T-butyl ether and crystallize it, filter, dry it, and package it. And there we go. So from this, it's a terrible yield, you may have noticed. It's like, let's go back to the recipe here. You can see that it's only a 33% yield, and I don't know. I think it's pretty suboptimal, but it's what we were dealing with, so that's what we're looking at. Now, you notice the side trains here as well. So we have, okay, first of all, we're making up the solution over in this train here. We'll talk about a little bit about why we did it this way, because you go, why don't I just do it in the reactor and think, well, maybe we will, but because of schedule, because there's a parallel operation going on here, and that allows us in the batch plan to understand better how to schedule the equipment. So sometimes it makes sense to do this, to show it this way, and then use that fact when we're making a batch plan. And here we're just making up, this is the quench solution. So this is just hydrochloric acid solution. So let's go down here and look at some of the details about this. So we come down here and you can see here's the thionyl chloride charge. And of course, once you start running this reaction, you need to be prepared to run through the scrubber, which the very first things you do is get the scrubber ready to operate here. And so it's all set to go. And we probably vent about 1.2 equivalents of this gas. We have to be ready for that. And we have to be sure that the scrubber is working correctly. So there's actually a monitor on it as well. And we come down to this step. Now, this step here, this is a contingent operation. Not too sure this is going to happen very often in reactor 2, where you have to add a kicker charge of thionyl chloride, but at least that's a potential, and so you have to think about that when you're thinking about your equipment set. And now we're down here in reactor 3. Now, reactor 3, we have yet another reactor that's involved. The object of using a third reactor in this case is that this keeps the main reactor, the reactors for the for the coupling steps dry. And so in this vessel, we're just simply doing a quench. Now that's going to give off gas. So this vessel definitely needs to have access to scrubber. So there's a lot of information that we're gathering about equipment here. How do we communicate that to the people who are designing the badge plan? So we do that through the equipment thing. So we say, okay, here's all the names here are place names, placeholder names. We're not, we don't know the name of the equipment that's going to be used. It may be done in several different places, actually. We don't know where when we're designing this. We're just setting it up. So what are the capabilities that are required? Well, okay, you're just telling people this is a volume. The capacity is done by volume. What type of equipment is it? That's what it is. And what do its characteristics have to be? Well, this one has to be resistant to halide corrosion, and it needs to have off-gas scrubbing. And same with all three reactors, actually. And the only thing is reactor 3, you need to be sure that it has convenient capability to do bottom face separations. That's what split means. Now, we can look at this full characteristics list. Didn't really assign anything to this reactor, but you can see this is there's all kinds of things you can add to it to be sure that you're communicating the requirements of the equipment to the people who are designing the batch plan. And again, down here, the scrubber, of course, it's a emission control device, and it has an installed sensor, the pH probe, and it's resistant to base because it's going to be filled with caustic. So that's what we did when we built the recipe. Is we also included the equipment requirements. Okay, so now let's look, how does that correspond to real world equipment? So let's go look at suites over here. Okay, so expand it out so it's easier to see. Now, the suite we're going to be talking about is called S1. It's in facility BDQ3, whatever that is, facility with good capacity for early steps, because this has got to be done at big scale. So you see we have equipment, stainless steel reactors, and of course that means its characteristic is going to be able to be resistant to base. So you just see all the capabilities that are here. These two reactors have off-gas capability. This reactor does not have off-gas. So this could pose a challenge. So we'll have to talk about how we're going to manage that when we start making the batch plan. And then you see we have the rest of the equipment is resistant to this one's Hastelloy, so it's got fluoride resistance, which we don't need in this case, but it's just a point that we're collecting the information about the characteristics of the equipment. Not that it's necessarily necessary for what we're going to do. It's just simply the equipment characteristics. Okay, let's go. Now now we kind of had a look at the suite, so you can kind of see how, okay, we're thinking about this one here. So now we're going to talk about batch plans. So when we're talking about batch plans, we have to, let me get there first of all. There we go. We ran out of real estate here. Okay, batch plans. So now I'm going to make it easier to find it here by putting in ones that are for the webinar. Okay, here we go. So this is a batch plan. So what you do to make a batch plan is you click this and you select a process, and then you give it a new name, and the folder is just in case you need to build some firewalls so you can segregate different information from the different users can work with the information, but they don't have to necessarily share it. Okay, so let's look at this. This is the process that we have built, and we're applying it to a suite. Now you can see all the information came over here, just like we had 100 kilo input, 66.84 kilo output. and we're going to apply to it S1, suite S1. Now, one of the things you're going to notice is that we had all relative units in the suite in the process. And over here we have real world units because we're in the real world now. We're making a batch plan. We don't have relative units anymore. Now we start talking about, okay, what does that mean? These are the units that will be. You'll also notice that things like this are going to be, we're going to be able to adjust the times, for example, of the operation. We can't change the quantities because that's changing the chemistry, but you can change the cycle times because they're going to be different at large scale. So you need to be able to adjust those in the plant. So let's start making assignments of equipment. So because now what we want to do is to see, well, do we have a fit here? Now we know that, for example, the vessels that really need to have off-gas capability are reactor 1, and the other one where we really need it is reactor 3. So let's make sure we pick vessels that we know have off-gas capability. Okay, and we mentioned before that R2 should really have it, but you can always, if we don't think it's going to happen very often that you need to add a kicker of thionyl chloride. So if that eventuality ever happens, what you might do is simply change your mitigation from being add more to move it to R1 and add more. So whatever vessel we've assigned to be R1, play as R1, in this case SRG 102, that would be the place where you would add it. So let's just say we don't need to have off gas for this capability right now. So let's put SRG 4 in there. Okay, there we are. Okay, so now you see it doesn't meet the off-gas capability, but we just discussed that. We knew that was going to happen. Now let's talk about this one. Okay, now I'm going to assign this to SRG4 because this is where the stuff is going to be anyway. And the reason for doing this when we start talking about the Gantt charts for the schedule for the equipment, you'll start understanding why we did it that way so that we can have ability to adjust the starting times for a parallel operation. Okay, here we go. These are kind of obvious. That's the scrubber. That's what that does. This one is going to be this unit here. It's a mixed tank. We don't need to be fancy, just a simple mixed tank. This glass line, you can see it's halide, acid and halide resistant. 104 is going to be, this is just in the way we're setting this up, this is stainless steel vessel, but at this point it's been quenched. You're just handling the methylene chloride liquor, so it's been washed. So it should be fine. We can bring it over and we didn't make any requirements for it. It's really just a whole vessel. We pass the washed methylene chloride to it and bring it back to R3, to whatever vessel, in this case, SRG 103, to do what needs to be done. And now we're going to go to the 101. Okay, now we're going to put this into the filter dryer. And this is its receiver. So this is where the mother liquor and wash is going. We're not going to bother with drums. Okay, so it looks reasonable. Okay, so now let's look down here, and now we start going, okay, now how big a batch do I want to run? Well, actually, what would be great would be if we could make 500 kilos in a batch. So let's enter that information here. And here we go. Now, you're going to see this really awkward number here. That's crazy. Now, really what you do when you're all done checking out your scales and things, you go back and make that 750 kilos input. But, that right now we're just kind of, okay, we're seeing if we have a process fit here. So let's go down and take a look at how we're doing. So if there's a problem with volumes, they'll show up as red text because we've overfilled it or underfilled it because there's a minimum agitation volume as well. So you can go down here like, uh-oh, we're in trouble. We're in big trouble in this vessel here, our R3 equivalent. So SRG 103 has only a capacity of 6,000 liters. Like, wow. Now, I'm just going to skip ahead a little bit here and tell you that the highest scale we can put into this unit is You can see why I have to mess with this a little bit. This sort of, so almost 300 kilos input, and see that'll fit, but that's not enough. See, that's kind of a problem for us. It's like, okay, well, that's bad. So, but this is from an off gas standpoint, this is the best arrangement. But okay, let's talk about, well, are we stuck with that? Well, not necessarily, because we can always modify our equipment so that it can be adequate. So let's talk about, well, okay, what's a better unit for R3? Well, maybe 104 is. So let's put 104 in there. 104 is big, by the way. See, 104's got 15,000 liters. And let's put 103 over here instead. Okay, now we put 103 over here. No, okay. So now what have we got? Let's have a look at that. And so of course it's going to be fine because it's huge. So for 200 kilos, it's fine. Let's put. Okay, how does it look for 500 kilos? Okay, it looks great. Plenty of room. But now we're in trouble in R2. Like, uh-oh, now what? So you're really starting to have it like, oh my goodness. So as it turns out, and I will just save you the drama and finding out how much we can get away with. About the best you can do is 350 kilos. Okay. So it's like, okay, so well, now what do we do? So we've already decided that we're going to have to put off-gas capability at 104. We have to add that to it. So another way to look at it is, well, we could just use 104 from the jump, right from the beginning, all the way through all the isolation and everything else. So let's put that in there and see what that looks like. So we got 104, put 104 in here. So 104 is running all the way through this thing. And so now what happens? How does that look? Let's put that in. And okay, well, that doesn't look. Let's take a look at that. Okay, so that fits. There's no problem. Now there's problems with volumes of receivers, but you know that you can discharge those as you go. So that's not really a a scale limiting issue for the receivers. But you see, you're going to have to remember that this vessel SRG 104 is going to have to be modified so that its off gas can be scrubbed. Okay, so we know that. Is that a big deal? Maybe, but probably not. So we'll just have to see. Now let's look at the Gantt chart down here. And like, okay, now one thing you're going to notice, okay, how we have 24/7 shop, it means we have 168 hours. And now let's count up the time that we're in this unit. So we go from 0 all the way out to 104 is still being used all the way out here. Now this is a little bit, okay, I just have to point out something. This is why we did this. Let me go back to the recipe and fix it, because we need to be kind of accurate here. So we don't really need to start this until about 2 hours into the process. This is where we start charging the solution to then the bromo pyridine to the bromoaniline to the operation. Okay, so that starts over here. So that's about 2 hours in. Okay, and then we look over here and it's about 30. So it's about 36 hours that we're in 104. And okay, so the longest time is about 36 hours in this operation. That means we can really only run about 4 batches a week. 5 is really kind of a stretch. So yes, we can get 500 kilos per batch, but we can only make 2,000 kilos per week because we're in this equipment too long. So what can we do about that? Is there anything we can do? Well, this is a fully capable unit here. This one is this one is just being used as kind of a whole tank going back and forth. We could maybe come up with a process that can use it to take some of the load off and allow us to run a bigger batch. And in fact, that's just exactly what we did. So I'm going to get back out of this again, and I'm not going to save it. So we'll just leave here for now. And let's go look at the other one here where we've already done the work. So I don't have to go through all of the assignment of the equipment. The equipment assignments are actually interestingly identical. We just changed the role of 104. And so 104 is now the crystallizer, where the solvent swaps and the crystallization is done. And so what happens then, let's go look at the Gantt chart here again. Okay, so this goes from 36 hours. You see, here we go. This is 104. And we finish up here at around this time, little over 20 hours. This one's around 22 hours itself. So this is where it's used as a swap tank back and forth with 104, and then we proceed to do the crystallization. And you see as a result, it's 22 hours. We can do 7 batches a week in here, and we get 3,500 kilos a week with this. So by looking at and observing how, the timelines we can maximize and changing the assignments of equipment use, we can figure out how to make much more, almost double the amount of material per week, because we have this very nice tool that allows us to make these assignments. So we just have to remember that we have to make the assignment and we have to make we have to make it 104 so that it has that scrubber capability. So let's have a look at are we really succeeding in all the things that we need to do with the okay. So the other thing about using 104 for the reactor, and this was an issue that we mentioned right from the beginning, 104 is now going to have to be dry before you turn it around. And we're using it for doing our extractions. So we're doing it for the quenching here. So that's an issue. So that means this thing needs to be turned around and dried out. Do we have time? Okay, well, here's the first batch of a series. Here would be the next batch of a series. So you kind of overlay the Gantt charts, and you can see that this is what's driving the timeline here is operations in the crystallizer and evaporator. And do we have enough time? Well, okay, here's where we end with 104, and here's where we start with 104. Is there enough time? And you can see there's a 6-hour gap between the start and the finish. That should be enough time to get that tank dried out and turned around. It's not an ideal situation, but it will allow us to use this equipment suite for the purposes of making 3,500 kilos per week of PPA. So thank you for your attention. And Dave, please.
Yeah, thanks, Ken. When you have all of your information all together in one place to easily align equipment for your process fit, you have what you need to succeed quickly and move forward with production. Automating the information, having an intuitive software platform, and limiting the time and mistakes that could happen is why SimpliDATA should be what you're using today. I want to thank you on behalf of Rondaxe for joining us today on the second webinar, and we look forward to seeing you very soon on the third.